All right, and you probably have seen that I have already built a YouTube playlist, so you guys can check out that list, or you can actually just bookmark that one, and then you can just check back on that. And I will try to upload the video ASAP, all right, as soon as. I mean, if I have time, then I will try to upload it pretty much like maybe a few hours after lecture. But sometimes I have to run out, and then it takes some time to render. So it might be like during the night of the day of the lecture. All right. So just wait for it a little bit. All right. I'll try to uh, get things up as soon as possible. All right, guys. So let's review what we did last time. We were looking at the thermal expansion. All right. And we were talking about how simple it is in terms of trying to explain the thermal expansion. When I say simple means we are trying to do things in just a linear fashion. So we don't care about the higher order term. We don't care about the cubic term. We sort of like, do some approximation here. So it doesn't matter you are talking about the volume expansion or you talking about just a linear expansion, which is just one-dimensional expansion. You use like the same type of equation. It looks like the same. Right, that's what it is. All right. So let's practice that one, and then we'll take a look at more exercises. All right, here. So a concrete sections of a certain superhighway are designed to have a length of 25 meters. So the sections are poured and cured at 10 degrees Celsius. So that's when they sort of like do the construction. It's already probably like at night or something like that. So what minimum spacing should the engineer leave between the sections to eliminate buckling if the concrete is to reach a temperature of 50 degrees Celsius? So it could be like, in the daytime, it's probably getting really hot. So, all right, so the idea is going to be pretty simple, right? Because what you know is, all right, so this is a concrete block, okay? And then, of course, you have to place them side by side. So you probably put tons of that. And because we are just looking at sort of like one dimension, which is just maybe just the length or just the width of this concrete block. So, I mean, just to be fair, it's supposed to extend on both sides. Does that make sense, guys? Because we haven't fixed any ends of this one, so it means it's free to expand. So it's probably expand on both sides. So we can assume that if the expansion happens to be delta L, so it's supposed to extend out half of that on the right side and the other half on the left. Does that make sense? Okay, so so the total expansion will be delta L. However, because you have to put them side by side, so it means you have to take into account that delta L over 2 from the neighboring block. All right, so that means the spacing, minimum spacing that you're supposed to leave between blocks, come back to delta L again. So it's twice of the delta L over 2. Does that make sense, guys? All right. So if that is good, then
Okay.
all we have to do is just calculating what is the linear expansion of the block and be done with. That's how simple it is. All right. So let's dive into it, shall we? So what we want is just the spacing needed is going to be the delta L that we can calculate from our expression here. The alpha, the linear expansion coefficient, can be found from the table. And this one, we just picked the one from the concrete value. Yeah. All right. So that's what we can do. And then you just multiply by the original length, the L0 or the L0. That is going to be 25 meter. Left the decimal places and everything, but it's just 25 here. And the delta T. Now you're starting from 10 degrees Celsius. You want to go up to 50 degrees Celsius. So the delta T that we are talking about over here is going to be plus 40 degrees Celsius, right? That is the change of the temperature. So you just plug it in there, and that's it, guys. You're done. All right.
Okay.
All right. So I know this is just a plug and play problem, so it's no big deal. All right. So this is just, how easy it is to implement this expression into a real problems here. All right. Try the next one, shall we? Okay. Move on. Here. This one is a little bit more challenging. All right.
Okay.
And this is more like this is like it's like college physics stuff. All right. And this one is challenging because in the sense that it's not numerical calculation anymore, but it's it's analytical question. A liquid has a density rho. All right. You guys know the density, right? By definition, the density is just mass per unit volume if we talk about three-dimensional stuff. All right, so that is the density. You can replace mass with maybe just using a symbol m, and the volume you could use v for that. Now they want you to show that the fractional change, okay, the fractional change is just like the change with respect to the original. So it's just right here. The fractional change is this. The delta rho over rho, that is a fractional change. In density for a change in temperature is given by the following expression. All right, how does it look? And what does the negative sign in this expression signify? That's the question. All right, you guys want to give it a shot and see how it goes? Okay, maybe you don't need that motivation here. It's too early, right? All right, it's like, all right, physics in the morning here. It's not really that early. Okay. All right, guys. So how are we going to approach this one? What do you think? Okay, so the way that I would like to introduce, the way to attack this problem is just we are going to utilize a little bit of calculus. I think seems to me that is the easiest way. The reason for that is because we would like to look at the change, right? The delta. And everyone know from calculus that every time you talk about the change, things get better and better when changing, the changes getting very small. Does that make sense to you? So what we saw before in here, what we have been discussing so far, we use the delta. And every time we use the delta, it's like a big change. And every time you talk about the big change, you just have to run into some approximation over here. That's approximation. Okay, so that's what we discussed last time, that we have to linearize. Okay, all right, John, I'm just going to throw away the higher order term because it's small enough. But if things are already small, that's even better. When I say that's even better means when things change at a very, very small, that change of the delta, the symbol that you use, turns into a differential change, the one that you used in calculus. And when you do that, that change is already small. So you can pretty much ignore the higher order term by itself because everything approaching zero. Does that make sense to you guys? This is approaching zero. We use this one a lot in calculus. All right, so what I'm going to do is I'm going to approach this problem from the perspective of calculus. Do things in the differential way. Do things in an infinitesimally small way. Does that make sense? All right. So what we're going to do is we're going to assume that all the changes that is happening is going to happen in an infinitesimally small way. So I'm starting with our expression of the density. It's mass per unit volume. That is your rho. Now, you want the rho to change with respect to what? You want to have it change it with respect to temperature, right? So what you need is actually what I'm going to do is you really want to do this. It's just like d of this rho with respect to the temperature. Does that make sense? This is actually, that's the goal. That's what you want. Okay, so if somehow you know how to do this, then everything will be nice and everything. Yeah, so you know the change of the rho with respect to the change in the temperature. Okay, however, as you can see from the right side, there is no temperature here yet, at least. It's not there. Okay, so that's why what we are trying to do is we would like to use the chain rule. Remember the chain rule, right? When you want to do the derivative with respect to one variable and it doesn't appear just yet, but you can chain it through that. And because what you are seeing over here is the rho is already in the function of v. So we are going to do the chain rule with respect to v instead. Cool? All right, so what I'm proposing to do is going to look something like this. So what you want is you want to take the derivative with respect to temperature. But because the function that you have in here is not in under function of t just yet. So what you can do is you can do d m over v by dv. And then you do the chain rule times dv by dt. Does that make sense? Cool. And now everyone knows how to do the derivative of this dude over here. M is just a constant. It's just a mass. It doesn't change anything. You can pull that m out. So all you have to do is just you do the derivative of 1 over v by dv. Cool. All right. Then what you have over here is, okay, I have dv by dt on the right over there. Okay. So what you have over here is you're going to get something that's can be done using derivatives of 1 over v. So it is a m times negative 1 over v squared. Cool? Already. All right, let me put everything in full detail over here. So this is how far you have come right there. But because we would like to explain everything in terms of the differential form, you can manipulate this term a bit by, you can think of it in the sense that we don't want to talk about derivative all the time. We just talk about the change of the row. So actually, you can see that you have dt on both sides. So these two can be pretty much cancel. I mean, well, speak briefly. We say cancel, even though mathematicians probably won't like that much, but we are going to do it anyway. All right. So we just assume that we're going to write everything down in terms of the differential. So I'm just going to erase those dt. We just talk about the change of the row with respect to the change of the dv. Oh, almost done. All right. And what you can see from here is you can see that now there's an m and there's a v square. So if you steal one of the v, plug it in the front, so it will look something like this. It's going to be m over v negative 1 over v dv. You're almost done here, guys. M over v is just a row originally. And then you can move this row to the left-hand side. So here comes almost done. D row over row, that's the left side of the equation, is going to be equal to negative 1 over v dv. But we already knew from thermal expansion that the dv in the differential form can be written as the beta v dt. Does that make sense? It looks long, but if you do it yourself without explaining, it's going to be short. Right? I'm explaining to you like using calculus and all this stuff. But anyway, so this is what it is. So I can rewrite dv as the beta v dt. And the good thing about this one is v cancel again. So that's it, guys. At the end, you get d rho over rho is just negative beta, okay, dt. And that's it. You are done.
Okay.
All right. When I say you're done, because what we have over here is the differential form, and then you can use this one as an approximated expression for the change or the delta. So that means it's a delta rho over rho is going to be negative beta delta t. You are done. It's kind of fun. All right. So you don't have to go through this crazy stuff like doing the chain rule and everything actually. So what you can really do is just taking the derivative of this row with respect to v right away if you want. Okay. But I'm just sort of like explaining the line of thought a little bit in the sense that, well, if you seeing this for the first time and you want to know what is going on with respect to temperature, you probably, attack this problem by taking the derivative with respect to the temperature right away. Okay, but for those of you that want to explore, all right, Wajan, why don't you just do the derivative with respect to v? Because you already see that the rho is in a function of v. And then you just express v as the beta v dt later. That is fine too. Okay, so there are a couple ways that you can approach this verification and all this stuff. All right, cool. It's fun enough. All right, so don't worry too much about this kind of question. It doesn't mean that it's going to be something that's going to show up in the exam a lot, because I'm not trying to prove this or prove that or on and on. But I think this is a good kind of like college levels questions that we're supposed to see this type of question from time to time. Okay, so there's a question comes in, should it be d rho equal to m over v negative 1 over v dv? Yeah, that is correct. Yeah.
John, on the right down, John, you wrote dv.
Oh. where? This dv where?
John, green.
Oh, is that here? Somewhere here?
The dv should be d rho. Or v.
Wait. This is still on the same line though. Am I right? This dv is belonging to this one here. Does that make sense?
Oh, okay. I'm confused.
At the same spot here. Is that right? Is that the right spot we're talking about?
Yeah.
Okay, cool. All right. So these are still together. All right. So my bad. Maybe I'm just writing it a little bit too far away. Okay. So let me rewrite this one more time. All right. DV. Here we go. Does that help? All right. Here we go. Cool. Thank you. All right. So next, try again. Okay. Just for fun. All right. So I think this is the question that I put it in the exams a lot because it's simple enough, but it's not like super simple. It's like not like a plug and play problems. You have to read, you have to set up some equations a little bit, but I mean, it's just easy for everyone to understand how to set things up. You have a poorly designed electric device, has two bolts attached to different parts of the device that almost touch, just like you're seeing in the figure. All right. So when they touch, all right, bad things happen. You short the circuit, everything, you know, you damage the whole thing. So if the initial gap between the ends of the bolts is given to be 5 micron, okay, at 27 degrees Celsius. So at what temperature will these bolts touch? Cool. You want to give it a shot and see what kind of equation you want to set up? It's just annoying. All right, so the easiest way to set things up is they're going to expand, right? Both steel bolts and brass bolts. So they are both expanding. So when gaps close up, it means that the expansion from both bolts gonna fill up that gap of 5 micron. So it means the gap of 5 micron is going to get contribution from the steel. So let me call it like a delta L of the steel. Cool. Plus, oh, delta, keep talking calculus here. Delta L from the steel. All right, don't need to do calculus here. Plus the delta L that you get from brass. Here we go. That's how easy it is to set it up. And because you already bolt is attached on a piece of whatever, a wall or whatever, you know, there's something you already attached. So it means the expansion is going to happen only in one side. Does that make sense? All right. So whatever the steel is going to expand is going to expand in one side. Whatever the brass is going to expand is going to expand on only one side over here. All right. So you don't have to worry about expand on both sides. So that's why I can just say just the summation of the two has to be equal to the 5 micron. And then what you can do is just saying that the delta L of the steel is going to be the alpha of the steel, because you care only the dimension, right? One single dimension that is changing. It's just the length of the bolt. So we just use alpha, linear length, times the original length of the steel. So let me call this the L0 of the steel. And now multiply by the change in temperature. Done. Plus, same thing, alpha for the brass, original length of that brass bolt, and delta T. They both having the same delta T. The temperature change is going to be the same, all right? So that's no big deal. So you can re-express the delta T to be, let's say they're going to touch at X degrees Celsius. So the temperature change is going to be 27 degrees, and then you do the X minus 27, okay? So before we move on, I think you guys know how to complete this problem. There's no big deal over here. But there's one tiny point that is so important, and I just want you to keep this in mind. Every time you talk about the delta change, you always take the final minus initial. You guys with me? Stick with this, all right? Stick with this rule all the time in science. All the time. The reason for this is because sign is very important. Okay, think about this. If I just want to talk about the change of the money in my pocket, let's say I come with like 100 baht in the morning, and if at the end of the day I have 90 baht, so what is the change? Yeah, everyone has to say it's a negative 10. Even though, I mean, you know, just a common conversation, you might say, okay, the change is 10 baht. But to be specific, because my change is in the negative direction, so I have to take the final amount of money, 90 baht, subtract out the initial money that I had, 100 baht. So it's a negative 10. On the other hand, if at the end of the day, I have 110 baht, so the change is going to be positive change. Okay. So the key point is you need to take the final minus initial all the time, because eventually you are going to end up with the opposite sign. And you will see later when we do thermodynamics, sign is super important. Positive and negative will mean opposite thing. All right. So this is just a short note for now. So what we have over here is, let's say we assume that they are going to touch at X degrees Celsius. So the change in temperature is going to be X minus 27 degrees Celsius. Cool. And that's it, guys. Just plug it in and you just solve the whole thing for X. Can I just stop here?
Okay.
Cool. All right. Because I mean, alpha of the steel, no problem. You can look it up in the table. Alpha of the brass, no problem. The initial length of the steel is right there, 0.01. Initial length of the brass is right there, 0.03. Delta T is already given here, so you should be able to solve for X, and you are done.
Okay.
Okay, then. All right, it's easy enough, I guess. All right, so this is what I would like to just sort of like, call it done for the topic of the thermal expansion. It's simple enough. It's just something that is just, get to know each other a little bit. And it's not, well, we're not get into the meat of physics just yet. All right, so that's what we're going to do next, guys. All right, it's just like, this is like warm up topic over here. All right, guys. So we're going to dive deeper into the stuff that is going to matter to us. Next stuff, let's talk about the states of matter just a little bit. All right, so just to give you some motivation, what kind of system that we're going to use in thermodynamic study. When you talk about the states of matter, you have three states that is very familiar to you: solid, liquid, and gas. Sure. All right. You might have heard of like plasma. Okay, but that's, you don't have to worry about that because plasma is not common state of matter. Well, as long as you're not living in like the sun or some superheated planet or whatever, plasma is not an issue here. So the solid, you guys know that is has a fixed shape, even though it has a fixed shape. But if you look in the microscopic level, the molecule or the atoms that build up that solid can shake a little bit. It can oscillate down, 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 down. Okay, so that's all right. Okay, it's doable.
Okay.
It's pretty good in terms of like the shape is kind of fixed and everything. You understand the thermal expansion will happen and on and on. But then that's it. That's it in the sense that the property of this one doesn't have any volume change much, because you saw from the expansion problem that the change is going to be minimum. So it's not a lot of fun when you want to track something down in terms of like the activity of things that is about to happen. So, well, solid is kind of cool, but right, just leave it there for now.
No.
Liquid, all right, this is kind of like, it's liquid, so it's tough because shape can change, depends on its container. The molecule can move around without any fixed position, but in terms of the volume, it doesn't change much, even though it might change more than solid, but it's still not a lot. Now, the greatest fun will happen in gas. The good thing about gas is it can pretty much fill up the container. So it's mean the volume is pretty much like it can change enormously. If you compress the gas, okay, the volume can change like multiple times. You can let the gas go into some big container. It's going to spread out, change of everything. So first, you can pretty much observe the volume change. All right, there are a lot of activity there. Second thing is you can actually eliminate the complications that might come up with the interactions between molecules. Does that make sense? The thing is, when these molecules are close by, they can interact with each other. And the interactions, all right, we can learn about that later. Like you can have like electromagnetic interactions. You can have like a Van der Waals interactions. You can, there's so many interactions that can happen when they're close by. Same thing happens with liquid. When they're close, they can have interaction among each other and things can go pretty crazy there. But now in gas, because you let them move freely and because the volume is kind of huge and the space between molecules are kind of like big, so you can come up with the approximation again, or at least some, theory that assume that the interaction between them is going to be pretty small. And that is going to be a good starting point for us to theorize everything. Okay, so the reason I'm trying to explain this slide is because of this. We're going to learn about gas a lot. And the reason for that is because you can pretty much observe so many changes, volume, pressure, things that I'm going to explain in a little bit later, but while ignoring the craziness of the interaction between molecules. Yeah, so you have a system that is simple enough for you to track the fine detail in the microscopic level, but then at the macroscopic level, you have enough changes that you can, have a lot of activity, you can have a lot of experiments that you can learn from it. So by picking gas to be your system of study, allow you to understand a lot of thermodynamics. Does it like a good point?
Okay.
All right. So it doesn't mean that thermodynamics does not apply to liquid and solids. They are all, actually thermodynamics apply to everything in this universe. However, studying gases, it's going to be the one that give you an easiest access to thermodynamics. And because beyond that, you already learned about ideal gas. Woohoo! Right? You already learned this from chemistry that, hey, Adan, actually the property of gases can be explained using a very simple expression as well. So why don't we take this one? Because solid doesn't have this kind of equation, liquid even worse. So let's attack ideal gas. Okay, so let's make it a good entry point. So we assume that if you have gas that has a low pressure or temperature is high enough, and we don't talk about the real gas. So that means if we talk about the ideal gas, so we can assume to be no intermolecular forces. Cool. So we did reduce complexity a lot. However, by having this no interactions doesn't mean that they cannot collide though. They can still run into each other and knock, and then you can use like conservation of momentum, right? Initial momentum equal to the final momentum, on and on. As long as the energies are conserved, there's no problem. Okay, the complication is not that bad, right? You allow them to knock each other out, transfer energy, transfer momentum, but assume everything doesn't take out any energy. So that means you assume to be elastic collision. Everything is fine. All right. And it's easy enough for you to track. All right. So enough for the motivation. So the whole point that I'm talking about over here is we are going to use ideal gas to be a system that we are going to learn thermodynamics from. Cool. All right. So using the ideal gas, what you can explain those gases is by using either states variables. All right. You can, all right, explain what kind of variables that you can use to explain gases. And then you combine that with a little bit of constants. You can pretty much describe states of gas very simply by, ta-da, here we go. If you guys remember this one.
Okay.
What kind of variables that you have used before with the gas? Well, guys, done pressure, familiar. Temperature, all right, we already learned from the starting point that temperature is pretty much our main characters over here in thermodynamics. Volume, that can be measured easily, the width, the height, the length, whatever. Number of molecules. We already had question asking you how many oxygen molecules are there around you. So that means it's going to be a huge, huge number. Million, and another million, I guess. Yeah, 10 to the 24, 25th, on and on. Or you might talk about mole, number of moles. That's going to be easiest for those that do that did chemistry, right? And 1 mole of gas is just 6.02 approximately times 10 to the 23rd molecules or atoms. Okay, so you can think of 1 mole to be just a conversion, unit conversion. Every that number 6.02 times 10 to the 23rd, that we'll call 1 mole. Okay, so this number right here, that is your Avogadro number, and we can symbolize it using the N with the subscript A. All right, so it's right here, Avogadro number right there. Cool. All right, now there are 2 more that I don't think we going to ever use it, but it might pop up from time to time, is the total mass. or maybe the molar mass, which is the mass per mole. The reason that we don't want to use this one anymore because, well, you can go back and talk about the amount of amount of mass whenever you like, once you know the number of mole or you know the number of molecules. Does that make sense? All right. But because gas is pretty much like, it's just spreading out, fill up the whole container. So it's kind of weird for you to take the gas and then weigh it on like a scale or something. All right. So usually, I mean, we can do it, but usually it's kind of like awkward to do in the everyday life. So it's like how many kilogram of oxygen around you. So, all right. So we can stop at the number of molecules or the number of moles. All right. I think that's good enough. Okay. So those are the variables that you can use. When you say variables, means these numbers can change. Pressure can go up, can go down. You can heat it up. Temperature can rise, can fall. Volume can expand, compress. So these are the numbers. You can get some gas leaks out, change the number of molecules, or you can, put some more gas into the system. You increase the number of moles, on and on. So these are the thermodynamics variable. Cool, guys? So far, so good with me? All right. Now, combine these variables with some constants that I'm going to introduce. You comes up with something that you might have already seen from chemistry. It's the equation of states. And what it states is state of ideal gas. So that means what we are talking right now is every ideal gas in the universe has to follow this equation. It doesn't matter what type of gas. It could be helium gas. It could be hydrogen. Usually hydrogen it's H2, but I mean, if it's like a monatomic ideal gas. So the thing is, what we want over here is we're going to assume it's going to be monatomic atom. So that means it's going to be a single molecules atoms. Okay, so it's going to be single. We don't want some internal structure. So that means H2 will not be qualified to use this equation. The oxygen O2, no. All right, maybe like NH3, no. All right, benzene, no. The complicated molecules won't be following this. We only care about the monatomic molecules or atoms. It's like a single particle over there. So mostly, I think the easiest way that you can think of is like a inert gas, like helium. That's good. Neon, something like that. It's like a single molecule there. The hydrogen is good, but maybe it's not common to have hydrogen in like atmospheric pressure. But I mean, if you only consider just a pure hydrogen atoms, that monatomic gas. Cool. All right. So if you focusing yourself only on a monatomic gas, it will follow this equation. Simple. P times V equal to nRT. Nice. Okay. The reason that I would like to focus on monatomic is just because it will eventually lead you to more expression that works for this monatomic gas. However, I mean, in reality, when we talk about diatomic like this, or you're going to do like more complicated atoms or molecules, actually, if you still assume the ideal gas situation, you can still use this equation. You guys see what I'm saying over here, yeah? So it doesn't mean that this equation only belongs to monatomic ideal gas. But what I'm saying over here is if you talk about only monatomic ideal gas, plus you impose the ideal gas situation over here, this equation or this equation of states works for ideal gas for sure. That's guaranteed. But then there will be a little bit, a couple more equations that is going to follow that will restrict yourself with just the monatomic situation. So that's why I think in this course over here, we're just gonna, confine ourselves with just monatomic ideal gas. Why not? Okay. And in the future, if you have to deal with, diatomic, triatomic, or some crazy molecules, then you can just, change or you just use more complicated expression. All right. But for us, ideal gas is good. You can always use this expression over here. And monatomic, it's even better because what comes next is going to be simple. Cool. All right. Now come back to this. So this equation is simple. It means the pressure and volume products, you take the pressure multiplied by the volume, is always equal to the temperature on the right-hand side Now the R that introducing over here, that is one of the constants that we are talking about. And then you have the number of mole in this equation, PV equal to nRT. The R that you have here is called gas constant, and it has a fixed value over here that's given. So that's done. All right. And somehow you can convert this. If you don't like, I don't want to talk about the number of mole. I want to talk about the number of atoms or number of molecules. What you can do is, we already knew that the number of mole is just the ratio between the actual numbers divided by the Avogadro numbers. You guys with me? This is good. Yeah, back here. The number of mole, the number of moles over here. You want to know how many moles are there? It's easy because you know 1 mole is this big. So you just take the total numbers of molecules divided by Avogadro number. That is the number of moles that you have in your system. Cool?
Okay.
All right. So with that, then you can turn the small n, the number of moles, take it as a ratio between the total number of molecules in your system divided by Avogadro number. And now you can see that if I zoom it in, R over N sub A is just the ratio between two constants. R is a gas constant, N sub A is just Avogadro number. So this will lead you to another constant, this ratio over here. And that is another constant called Boltzmann's constant. Cool?
Okay.
All right. But in terms of the structure, they are exactly the same. It's still P times V equal to the amount of gas in the system. It can be either number of moles or number of molecules. And then you end up with the temperature on the right-hand side. And then you just have to make sure that you pick the correct constant to use. If you use the number of moles, you just pick the gas constant. If you use the number of molecule, you just use the Boltzmann constant. And that's it. Okay, so maybe I'm speaking too much in terms of like equation of states. You guys probably have seen this already a couple of times. All right, but let's say this is the relationship that any ideal gas has to follow. PV equal to nRT or PV equal to capital NKT. Cool. All right, and don't forget the temperature that we are using here has to be now in an absolute scale. So that means everything has to be in Kelvin, because now it's a substitution of the temperature. It's not like a change of the temperature anymore. If you talk about just the change, that's fine. You can talk about the change in Celsius or change in Kelvin. They have the same amount of temperature change. But in this equation, you want the value of the temperature. So now you need temperature in Kelvin scale. Cool?
Okay.
All right. And before we move on to any complicated stuff, good thing about this equation is you can use this equation to explain any state of gases, right? So that means sometimes if you want to compare two conditions, for example, you might take a gas molecule and then you somehow expand the gas, compress the gas, raise the temperature of the gas, or whatever. You can do anything with it, but as long as you have a closed system, so it means your system is already been taken care of, you take care of everything in your system, PV equal to nRT all the time. So that means if you have a system that doesn't have any leaks, so it means you're talking about the same amount of gas in your hand. Let's say you bring in this amount of gas and it doesn't have any additional gas later, or you don't take away any gas from it. So you can see that PV over T equal to N times R. Make sense? So on the right-hand side, this is going to be constant, doesn't change. So that means as long as your gas in the system does not change, PV over T must stay fixed. So that's why you can compare two states of the gas simply by taking the PV over T and compare to PV over T in another state or in another system, another environment or another setup, on and on. Cool. All right, so I think this is a good enough refreshment of, for those of you that had already done chemistry. So this is a PV equal to nRT, equation of state. But for those of you that haven't done anything of this, don't worry about it. I'm just confirming that this is just an expression that you can always apply to any ideal gas system. It has to follow this equation all the time. Okay, you just pick, you want to use the n, the small n, or you want to use capital N. You just pick constants accordingly. That's all. Is it good enough? I guess. Not confusing you in any way. All right. So if that is the case, let's practice a couple of exercises and then we take a break. Sounds good? All right. So it's kind of enjoyable today. Yeah. All right. An ideal gas occupies a volume of 100 cubic centimeter at 20 degrees Celsius and a pressure of, what was that? 1, 2, 3, 4, 10 to the fifth Pascal. There you go. All right. So you already are given, information about gas. Now determine the number of moles of gas in this container. See, they want the number of moles. So what they want to know is what is the small n. So if that is the case, that is easy, guys. PV equal to N or T. So that means the number of mole is just the pressure times the volume over the constant, gas constant, and temperature. So the purpose of this problem is I just want to make sure that you guys have to convert the unit properly. Look at this. Pressure, Pascal is good. I think you guys took fluid dynamics from physics 1, right? Pascal is the SI system for the pressure. It's the Newton per square meter. So that's good. I can put 10 to the fifth here, Pascal, for the pressure. Now look at the volume. Oh, it's cubic centimeter. So you have to convert this to cubic meter. How do you do that? How do you do it? All right, because it's a cubic centimeter, you want to go to a cubic meter, you're supposed to multiply by 10 to the negative 6. I don't know you got this or not. If not, wait for it. I'll have some trick for you if you like that. All right, let me complete this one. R is R. I can just leave it R there. I mean, you can look it up. It's 8.31. You can plug in the number. And now the temperature is 20 degrees Celsius. And don't forget, you have to plug in the Kelvin temperature over here. So it's going to be 273 plus 20, and it's in Kelvin scale. And that's it, guys. You can calculate the number of moles right there. You are done.
Okay.
Cool. And now, if you want to figure out the total number of molecules, so that's your capital N, all right, that's no big deal. You just use PV equal to capital N K T. All right, it's a K sub B, or sometimes they just talk about K. They are meaning Boltzmann constant there. So same thing, capital N is going to be P times V over Boltzmann constant T. So you should be able to do exactly the same thing. Just pick the Boltzmann constant instead of gas constant R, and you will be able to figure out capital N. Cool? All right. So now let's, before we leave this problem over here, unit conversion, guys. When you want to go cubic centimeter and turn into cubic meter, how did you do it? How did you do it? All right. My approach is this. I don't know if you like this or not, but this is what I have been using my whole life. You guys know the C, the centi already, right? C is 10 to the negative 3, right? Oh, sorry, 10 to the negative 2. Milli is 10 to the negative 3. Maybe you have like a micron, micro, 10 to the negative 6. Nano, 10 to the negative 9. And this one works all the way to positive exponent, doesn't matter. You can do kilo, 10 to the 3rd. You can do mega, 10 to the 6th, on and on. Giga, 10 to the 9, blah, blah, blah. So these are all the prefix. So to me, this is just a number.
Okay.
This is just a number.
Okay.
One more time. This is just a number.
Okay.
So what I'm seeing over here is this. When you use centimeter, it's the same thing as you have a centi multiplied by the meter. Does that make sense? It's just a number. So I can do this centi cube times meter cube. And the centi cube is just 10 to the negative 6. That's how easy it is for me to convert between units. Okay, for example, one more time. If I start from cubic meter, well, hey, Ajahn, I want a cube, what is that? Nano cube. Is that, I don't know, is that the unit or not? I want to turn this into nano cube. So how do you do it? You just multiply by n divided by n. See, you haven't done anything with me. So you treat all the prefixes as numbers. This is a number. So you want nanometer cube, fine. Keep the nanometer in there. And then you have nano cube out here. And nano is 10 to the negative 9. To cube that, so it's then 10 to the negative 27. Flip it up top. So something like that. Does that make sense? All right.
Okay.
I don't know if this works for you or not, but if you like this one, just take it. But if you already had a way that you can convert between, you know, units, like you go smaller, you go bigger, use your own. But this is the way that I approach the unit conversion. And it seems like it gave me a very, very small mistakes over time. Okay, I can do a very complicated unit conversion without any problem. And I don't have to come up with like big to small. I have to multiply, small to big. I have to divide on and on. All right, it's just my 2 cents here. Okay, all right, guys. So I think nano is 10 to the negative 9. Correct. Yes, yes. Very good. Yeah. Oh, okay. Yeah. 9. Thank you. Yeah. All right. I just want to make sure that you guys like looking at the slide, yeah, or not.
Okay.
Okay. Thank you. Yeah, it's 10 to the negative 9. Sorry. Yeah, sorry, my bad. All right. All right, guys. So I think this is a good place to stop. All right. So we'll take a quick 10-minute break. Sounds good. All right. We'll come back with more exercises over here. But for those of you that want to dive in a little bit earlier, you can just read these problems and then we'll come back and solve this problem together after the break. All right, guys. So take 10. I'll see you in 10 minutes or so. All right.
Okay.
So let's take this one. So the next example is this. You have a pure helium gas is admitted into a tank containing a movable, right? So there's a moving piston there. So it means you can pretty much adjust the volume. Now the initial volume, pressure, and temperature of the gas are given there. And if the volume is increased to a new value, pressure to a new value, they want to know what is the final temperature of the helium gas. You see what I'm saying here? This is exactly what I told you about. You have a system of gas. It doesn't change in quantity. There's no addition of the gas. There's no, take away of any gases, anything. It's just the same amount of gas. So what you know right away is you can use PV over T is always a constant. Make sense? Or that means you can compare two conditions, two states, two environment or whatever by taking this expression over here, P1 V1 over T1 equal to P2 V2 over T2 all the time. This one works. All right. And the good thing about this one is as long as you're comparing the same units between pairs of variables, that means, for example, if you already had the kilopascal here, you don't need to do any changes if the other value is also in the same units. Does that make sense? Right? So this is a nice thing about it. So as long as the units are coincide between left and right side, you are good to go, except you have to make sure that you use the Kelvin unit for the temperature, right? Because, well, converting from Celsius to Kelvin, you're adding some number. You're not multiplying. You're not doing units conversion by multiplication. You do it through addition. So that won't work. You still have to use Kelvin scale for temperature all the time. Okay. Already. So with that, let's give it a shot. So let me call whatever going on first to be my first condition. And after the change, that is going to be our second condition. Okay. And then all you need to do is just plug in the number. All right. The pressure initially is 200 kilopascal. 200 kilopascal. That's P1. Okay. V1, that is the volume originally, that is 15 times 10 to the negative 3. That's good. Cubic meter. Divided by temperature is already given in Kelvin. That's nice. Perfect. Done on the left side. Now look at the second condition. Now you have a new pressure, which is increased. That is fine. You just put 350, same units, kilopascal. That's good. Okay. And the next one is new volume. Put it there. Same units already. That's nice. And that's it. You just have to figure out T2 and you are done.
Okay.
Cool. All right. So that's how easy it is to apply the equation of states or use the equation of states to compare between two conditions of the gas when the gas does not change in quantity. All right, guys. So that's good enough. So far, so good. Keep going. All right. Any questions so far? Seems easy enough. Yeah. All right. So now it's time for us to talk about heat. All right. And I remember that last time somebody talked about heat a little bit in connections with the temperature discussion. And now we are going to demystify what is heat by asking you first, how do you feel about this one? The word heat energy. You like this or not? That's the question. Is the sound effects too loud? I don't know. Everything changes now. So I don't know. Okay. It's fine. Okay. So how do you feel about this word, guys? Heat energy. It's fine. Or, something fishy, or, you feel a little bit weird now. All right. So fishy. Yeah, fishy. Very good. Fishy is good. So for those of you that try to translate this one in Thai, it might not feel anything, because if I try to translate this one in Thai, it will just say it's the พลังงานความร้อน heat mean ความร้อน and energy mean พลังงาน yeah, so it's พลังงานความร้อนis okay, but it turns out that's not right. What's right about this word, I mean, to be perfectly correct, it's supposed to be thermal. That means พลังงานความร้อน actually. So it's an energy that related to temperature. That is a thermal energy. The reason that heat energy doesn't work, and it shouldn't work at all, because here we go, guys. This is the key. Heat is energy transfer. Okay. Heat is energy transfer. So this is the reason why if I'm going to say heat energy, it's going to be the energy of energy transfer. That doesn't make sense. Okay. So that's the key. The key is heat. It turns out to be the amount of energy that gets transferred from one place to another place. So it has some dynamics, or it has some movements going on. That's called heat. Okay. So if you want to talk about the energy that is due to an object is having some temperature, that has to be referred to as thermal energy. Like your body right now, 37 degrees Celsius, that means you have some energy of your own. We already said that temperature means energy. So because you have your body temperature of 37 degrees Celsius, it means you already possess some energy in you. So that's why you have non-zero temperature, right? Right? So that's what it is. So that's what means by heat. It's the transfer of energy, and to be specific, due to the temperature difference. When I say due to the temperature difference, because of this, I want to just talk about it right now, guys. Have you heard of this energy transfer before? What else in physics that you had done before that talked about energy transfer? What kind of quantity, what kind of parameters, what kind of physical stuff that you did, and then it means energy transfer in the past? What do you think? Anything? What kind of like physics variables, parameters, quantities, or whatever? Oh, potential into kinetic. Oh, something is there, something is there. All right, so the potential energy turns into kinetic energy, that is the energy transform. but it's not transferred just yet, but it's transformed from one form to another form. But there is another one that actually talking about the energy transfer, like I transferring something to you, I transferring something to the object. Collision. Collision is energy transfer associated with the collision, right? Because it's changing. But then when you talk about the collision, then it's transferred due to the momentum change, maybe, probably, yeah. But you can talk about the energy transfer due to the collision as well. Very good. What is the quantity that actually associated with that kind of energy transfer? In the collision, usually you said it's a momentum transfer, and that leads to the energy change, right? Because momentum gets transferred to the other object. There is another one that actually directly hits onto the energy transfer, guys. One more. Conduction. All right. Heat conduction. This is like, okay, this is like a script over here. We're going to learn about heat conduction in a little bit later. But that is still related to heat. And that is some sort of like a heat transfer mechanism. That's a heat conduction. All right, here we go. You are going to be, and I don't need that one, work. Any clue here? It's kind of like, no. It's not that big. So work. If you remember, you already defined it as like W equal to F dot S. Does it sound familiar, you guys? Oh yeah, work. Yeah. So when you talk about work, it means like you're pushing something, you're pulling something, and then that thing that's supposed to be, for example, if you push something that already stationary, and eventually it can move. So it means when it's stationary, it has zero kinetic energy. But once you push it, it's gets some velocity. So it means it has some kinetic energy that is non-zero. The reason that it gain more energy is because you transfer energy to that object by means of work. Cool? All right. So the reason I want to mention about work at this slide right now is because now you have two things that can do the same stuff here. You can do energy transfer either by heat or either by work. You already studied work in Newtonian physics. That is fine. Now we are going to do the same business here, but using heat. Is the energy transfer due to temperature difference? All right. And I hope you have a clearer picture when we talk about thermodynamics soon, very soon. But for now, let's bring us back to the business of heat at this point. All right. And we are going to talk about work maybe next lecture. Okay. All right. So just to conclude over here, heat is not energy contained inside a body. Because if you want that one, that means thermal energy. That is the amount of energy contained in the body. That's thermal energy. However, the heat is the transfer. But then you don't want to talk about, heat containing inside a body is the total kinetic energy of those stuff in this. I mean, it's a long sentence to explain the total energy of the system. So we come up with a very sort of like an easy word to represent the whole energy of the system. We're going to call them internal energy of the body. Does that make sense? All right. So that means if, let's say one more time, my body temperature is 37 degrees Celsius, you guys know that I must have some kinetic energy of all the molecules in the body of mine. So total amount of kinetic energy that I have, I can sort of like collectively call them my internal energy. Cool. All right. So from now on, every time we talk about the kinetic, every time we talk about internal energy, you can think in your head, it's like it's just the total kinetic energy of the system. Pretty much the same thing. All right. Okay. Now, with that, so because now we know heat is just energy transfer, so the units of heat must be the same thing as the units of energy. So it must be in the units of joule. Or if you want to use calorie, that is fine. They are the same thing. It's just converting through 1 calorie is 2.4 joules. That's all. Okay. All right, guys. So that's what heat is about. But now, what we saw before was this. Back in the day, we didn't know that heat and work are the same thing. And we didn't know that actually heat related to the energy because we don't really know what heat was back in the day. So experiments by James Joule, right? Joule, that the unit that we use by his name, is he conducted an experiment just showcasing that you can change the gravitational energy, the mgh, you turn into the thermal energy. So that means you can raise the temperature of the water in a tank. And this experiment was done like using like a huge amount of mass hanging at like above the ground, and then you drop the mass and then have the paddles just turn inside a water tank, and then the temperature of the water in the tank raised by, you know, maybe a fraction of a degree or something like that. All right, so that was the first experiment that showcased that, yeah, thermal energy is just related. It's another type of energy that you can link to some mechanical energy back then. Okay, so today there's no surprises or anything anymore.
Okay.
It's just good. You know, energy is energy. It can be in many, many forms. All right, so that's what it is. All right, before we move on, just a quick, you know, just quick stop at the food calorie, just in case. When you look at the food packaging, even though you see the same calorie, but you have to notice that the C over there is a capital C. So with that 230 calorie in the food packaging over there, it's mean 230,000 calorie. Okay, so that means one food calorie is 1,000 cal that we use in our calculation here. Okay, very good. And the good thing is, if you look at the European, I think is a EU packaging, the good thing is they quote all the nutrition facts in joules and in kilocal. So it's very scientific there.
Okay.
That's kind of nice. Okay. All right. Just comparison. Okay. Right. Come back to us here. So what we want to do today, all right, before we move on and talking about the business of heat in thermodynamics, we just want you guys to familiar with heat first. So the easiest way to think about heat is because it's just the energy transfer. And because now we understand that the energy is directly linked to temperature. So there's no doubt. If you pretty much know how much energy gets transferred through heat. So let me call that as a Q. So Q is the amount of energy that gets transferred. So I can draw a figure to represent things that is going on here. So you might have an object over here and you transfer some heat into it. That is the Q. Okay, so there are two directions that it can happen. You can transfer heat into the system, or you can extract heat out of the system. See that? There are two directions going on. So in the near future, we are going to define the directions of the heat flow. All right, but logically, something that flow in, it's just like you adding something to your system that is going to be positive heat. On the other hand, if you steal some heat away from the system, that's supposed to be negative heat. Does that make sense? All right. And things get a little bit better when you talk about this. The consequence of having some heat flow into the system, you should be able to notice the increase in temperature. Does that make sense?
Okay.
Yeah. On the other hand, if you extract some heat out from your system, you should be able to observe the lowering of the temperature. So what I'm saying over here is the amount of energy that flow in or out should be proportional to the change of the temperature in your system. Cool. But then how big is that? You can turn this relationship into an equation by introducing a constant in front of it. And that constant that shows up right here is good, because this will give you amount of energy that requires for you to change the temperature by delta T. So that constant that shows up here, we would like to call it the heat capacity. Does that make sense? Okay, heat capacity. It's the capacity of the amount of energy that gets transferred to the objects. The reason that it's called heat capacity is this. Think about this one, guys. If the C is big, let me draw it like this. With the fixed amount of heat, Q, if C is big, then that means your delta T must be small. Does that make sense? On the other hand, if C is small, So delta T must be big. I'm writing like this. I don't know if that makes sense to you or not. But that's what it is. So look at the first case. When the C is huge, it means it has a big capacity. When you have a big capacity, you shouldn't see a lot of change in temperature. You can imagine this like your stomach when you're eating some food. If you have like a big stomach, so it means your food capacity is huge. So it would take a lot of food for you to be able to feel full. The feeling, the degree of fullness is temperature, right? So if you have a very big stomach to store food, so it would take a lot of food for you to be able to increase your degree of fullness. I don't know if my analogy work or not. Right. On the other hand, if you have a super tiny stomach, so you just eat a little bit, you already are, all right, I feel full already. Does that make sense? All right. So that's why the capacity, the C, is just something that allow you to tell how big of the energy that you can store in an object. And that links directly to what is going to be the change in the temperature from that energy transfer. All right. So that's heat capacity. However, this is an inconvenience quantity to use. Why is that? The reason is because heat capacity, it depending on the amount of the object. When I say the amount, mean, for example, if you want to talk about the capacity of water, you have to ask me back, well, Ajahn, how much water are you talking about? You want like 1 kilogram of water, or you said like 1,000 kilogram of water? You just talk about a gram of water. If you take a fraction of water, of course, the heat capacity will be super small because you have a tiny amount of water. But if you bring in a tank of water, it's going to be huge capacity because the amount is big. But then you say, well, Ajahn, they all water. Why do you have to worry about the amount? Why don't you just come up with an idea that, yeah, it's a capacity of water. And then you talk about the amounts later. Does that make sense? Yeah. So what we are trying to say is, why don't we define the capacity per unit mass? That would be the easiest, or that would be the most universal quantity that you can use for any water in the universe, pretty much. So that's why we are going to introduce the specific heat. So it depends on the type of the substance, because you define the specific heat to be heat capacity per unit mass. So if you bring in 1 kilogram of water, they will have exactly this same amount of specific, same amount of heat capacity, because it's perfectly 1 kilogram. All right. And then you can take this 1 kilogram anywhere you like in this universe. It will have exactly the same heat capacity. Does that make sense? So let's define the specific heat. So now we know we can talk about just the substance itself. For example, water. Where's water? Here you go. So no matter where you are in this universe, the water, if you bring in 1 kilogram, it will have the heat capacity of this big, approximately about like 4,200 joule per kilogram. Or if you want to talk about calorie units, it's going to be 1 calorie per gram. That's it. It's done. And later, if you bring in how many kilogram of water, whatever, you just multiply that with the mass. And then you get back to the heat capacity of that total amount. Does that make sense to you guys?
Okay.
And this is the reason why we're going to re-express our heat capacity of that object by a product between the mass of that object times the specific heat of that mass. And then you just look up the table, what type of substance that made up that object, and then you just use the specific heat of that substance and plug it in. So you come up with the equation that look like this. I think it looks familiar to you guys. Q equal to MC delta T. To share up that much. Okay, cool. So I hope you sort of like see what this equation is about. It's just energy transfer. So from now you have a mass, M. You can transfer heat to it. Bam, that's a positive heat transfer. Or you can extract some heat out of it. That is going to be a negative heat transfer. And good thing about this equation is when you take some heat into the object, the delta T will be positive along with the Q. So this equation is good because the sign of the Q and the sign of the delta T are going to be exactly the same. So that means if you take out the heat, the Q will be negative, the delta T also be negative. So it means your temperature will drop after you take away some energy from the object. See, so that's why I am emphasizing of using the sign all the time. Make sure that you stick with the rule. The change is always final minus initial conditions all the time. All right. It would be more stuff than this, right? But for now, I think this is good. All right. So with this idea, let me ask you a simple question. If you go to the beach, to the sea, and then you're standing on the beach, then you, of course, the most contrasting substance that you're seeing is either sand or water, right? Which one has a bigger specific heat? What do you think, guys? No need. I don't know, sound effect much. Water, very good. Water, very good. All right, guys. So nice. So the reason that the water has a higher specific heat is because you guys know when you're standing on the sand feel hotter to your feet, right? But when you run into the water, it's a little bit cooler. So the reason that the water is cooler is because, of course, it has a higher specific heat. Sand and water receive the same amount of energy from the sun. Okay. But then the reason that the water is feeling cooler because it has higher heat capacity. So that's why the temperature rise is a little bit smaller. The sand is like a solid stuff, it doesn't have any way that you can store a lot of energy. So it has a smaller heat capacity. So that's why temperature is going to be rising so much. Cool. All right. So I hope you understand the concept of heat capacity. Okay. So far, so good. Now try this one. This is a plug and play example over here. The temperature of a silver bar rises by 10 degrees Celsius when it absorbs this much energy. It's in kilojoule of heat. Now the mass of the bar is given to be 525 grams. Determine the specific heat of silver. All right. So this is going to be a straightforward plug and play. Q equal to MC delta T. Make sure to use the correct units. Okay. Heat is 1.24 kilo, 10 to the third joule. The mass, don't forget to turn it into kilogram. So you divide it by 1,000. C, this is what you want. C of the silver. Okay. And delta T, yeah, definitely it's going to be 10. Over here, even though in your head, they're both positive over here, right? Because we assume that it's absorbed. So it means there is the heat of this much transferred to the object. So the temperature is going to be raised by 10 degrees. All right. And from here, you will be able to figure out the C of the silver and you're done. All right. So this is a plug and play thing. Okay. No big deal. So what's interesting about this whole business of the specific heat and heat capacity here is this. All right. Try again. So this is a very realistic questions. And I think this is very current because you guys, maybe some of you has already tried to install solar panel, maybe. All right, we'll see. So you say you have a water heater and it's operated by solar power. If the solar collector has an area of 6 square meter, all right, so you have a solar panel and the intensity, okay, even though you don't know this particular definition of the intensity, you can observe from the units. The intensity of the sunlight is 550 watts per square meter. So that means you get a power of this much, 550 watts per square meter of the panel. Doesn't have to be panel, but I mean per square meter on the surface of the earth. So what you have over here is you have a panel of 6 square meter. So that's 6 square meter. So the total amount of energy that you receive from the sun, total power, sorry, I said energy, power is going to be just taking the intensity and then you just multiply by the area. Does that make sense? Because the intensity is just the power per unit area. Now you have 6 square meter, multiply by 6, you get the total power. So at least now you know your panel can give the power of 550 times 6 watts. Okay, so that's good. That's the power of your panel. Now, how long does it take to increase the temperature of a cubic meter of water from 20 to 60 degrees Celsius? So what you want, I mean, the known information is the temperature change is definitely positive 40 degrees Celsius. That's fine. No big deal. Now, what you want to know is how long does it take? So you want to know time. So let me call delta small t over here. How much? Now, do you know the mass of the water? Well, no big deal. It's a cubic meter of water. What should be the mass of water if you have a cubic meter of water? The mass of water. What's the mass? You guys still with me, yeah? So what's the mass of a cubic meter of water? That's gonna be huge, I guess. Right, because you guys know it's a, I think the known conversion factor is 1 gram is from a cubic centimeter, 1 cc, right? Cubic centimeter. So very good. There you go. It's 1 ton, so 1,000 kilogram. So that is the mass of this cubic meter water. Cool. So that's it, guys. So now we can execute Q equal to MC delta T. Okay, mass is now 1,000 kilogram. C of water, you can look it up from the table. Okay, let me pull C of water here. Delta T is 40 degrees Celsius. Now, what about Q? Well, no big deal, John, because from the definition of power, power is just energy per unit time, is energy per unit time. Okay, so that means, all right, the amount of energy over here, this is the Q that we're talking about, is the energy that eventually going to get transferred to warm up the water. So you can express this one as Q over delta T equal to the power, or Q is just power times delta T if you want to. All right, you know the power already. So that means you can re-express Q as the power times the amount of time that it takes to warm this whole thing up. And that's it, guys. So delta T is just this whole thing over here. And you're done.
Okay.
All right. So I think this is good enough, I guess. All right. So you can crunch the number later if you like. Okay. But I think this is something that's simple. And I think you will find out it will take a lot of time, of course, because I mean, using solar panel to warm up the water, I don't think that's a good way of using your energy wisely at this point, because maybe the solar panel is still not that, I mean, it's still very efficient at this point in comparison to what happens last decades, but it's still, all right, you need like a big panel. So 6 square meter, probably that's going to take you hours to warm up water of what, 1,000 kilogram of water. That takes a lot of energy there. Okay, cool. All right. So this is a very, something that's applicable to real life. You can use this techniques or whatever things to calculate the amount of energy required to warm things up, on and on. All right, cool. Guys, last stuff that we want to talk today, and just to wrap up things about the heat transfer to an object here, is sometimes, you might not hit the range of the temperature that energy transfer means temperature change all the time. Why? Because sometimes you might be looking at the point in temperature where you are looking at the phase transition. Does that make sense? So when you hit the phase transition temperature, the amount of energy that you put into your system going to be used to change the phase. For example, if you want to vaporize water, for example. So it means, everyone knows that water is boiling at 100 degrees Celsius. So that's no big deal. So that means if you are right at 100 degrees Celsius, you can keep pouring in energy into the water. You're not gonna raise the temperature any further, because the energy that you pour in going to be used to vaporize water. See? So that means at that point, the temperature will be fixed at 100 degrees Celsius. And that we call the transition temperature. So that means the energy that you throw into your system won't be reflected in terms of the temperature change, but it's going to be reflected in terms of the amount of phase transition of that substance. So we call this process to be the phase transition, and the amount of energy required for that transition, we call it the latent heat. The latent, it just means hidden. The reason it's called hidden because you won't see temperature change. It's hidden there. All right. So what you can calculate is going to be simple. If you know the amount of heat that required to change the phase per kilogram. Once again, we do everything per kilogram. Why not, right? So if you know the amount of heat required to transition the phase by 1 kilogram, so all you need to do is just take the amount in kilogram M and then multiply. What did I do? Okay. And then just take the amount in kilogram and then just multiply by that latent heat, the amount of heat that allow you to do the phase transition per kilogram. And that's it. This product will give you the amount of energy required to do that phase transition. Cool. All right. So this is very simple in the sense that when you have a phase transition, there's no need to calculate any temperature change because there's none. The only thing that you need to calculate is how much or amount of mass that get phase transition. That's all. Okay. So the equation looks very simple. It's just mass times the latent heat. Okay. And then you can have a name for it. You can say, hey, if you have solid turn into liquid, you can say, you can call that is the heat of fusion. And if you go opposite way, if you want to turn liquid into solid, that is going to be heat of solid. Oops, sorry, guys. Forgot to turn off the sound here. Okay, so if you go from liquid to solid, that will be the heat of solidification. All right, so that's cool. Now, if you want to go different transition, you might want to go from liquid to gas. So everyone's familiar with this one, is the heat of vaporization. Okay, if you want to go opposite way, everyone knows this one as well, is the condensation. All right, so that is going to be heat of condensation. Cool. All right, then. So that is the additional stuff that you need to know when you are right at the transition temperature. You won't see any delta T. All right, you only can calculate the amount of substance that get transitions. All right, guys. So that are the two main equations that you are going to use. And this table will give you the latent heats of a couple of substances that you can refer to this table if you want to look up some numbers over here. Okay. All right, cool. All right, guys. Can you give me a second here? It's like bugging me here. All right, guys. Hey, come back to our business over here. All right. So this curve right here just showcase the total stuff that happens to water, all right, the one that we familiar the most. So you can start from, here we go. So you have like a super low ice. So this is like a deep frozen ice at the -30. So let's say, assuming that you transfer constant rate of energy to it. So the horizontal axis over here is the energy added in joule. So you just sort of constantly adding energy to this water and see what happens to it. So as you can see, initially, you're going to raise the temperature of the deep cooling ice over here. So that means during this first portion over here, you will see the temperature rising. With me, guys? All right, so it's going to get higher and higher in temperature. Now it's going to hit 0 degrees Celsius. Right there, you start with the heat, the phase transition. You start to melt the ice. So this portion over here, that is when you're using Q equal to ML. So let me note on here. That's Q equal to ML. Over here, this is Q equal to MC of ice delta T. Cool. All right. Once you keep melting the ice, once all the ice has been melted, then you start raising the temperature one more time. So now it's a liquid water, but then the more energy you give to the water, the higher the temperature will change. And you get higher and higher in energy, in temperature, sorry, until you hit 100 degrees Celsius when you hit another phase transition, when you do a vaporization. So at 100 degrees Celsius, the energy that you are given to, that's been given to the water will be used to change the phase. So it's just vaporizing water. So more water will turn into vapor. Okay, so you turn everything into vapor, you vaporize it until all of those liquid water has been vaporized. So during this phase, one more time, you're going to apply Q equal to ML, but it's going to be different L. This is going to be L of vaporization. This is going to be L of the solidification. And during this phase over here, you're going to do Q equal to MC of liquid water delta T, something like that. All right. And after you vaporize everything, there will be no more liquid water. They are purely in gas phase. Then you just keep going, just if you want to. So it's going to be superheated water if you want. So once again, if you hit this phase, it's going to be once again Q equal to MC of vapor delta T, on and on. Cool?
Okay.
All right. So this is a complete picture of, it doesn't have to be water. It could be any substance that, well, behave regularly. That's go through solid, liquid, and gas phase. Yeah, it will show up the curve just like this, but of course, at different transition temperatures. Okay. But as you probably, you guys wondering, like, Ajahn, there are some substance that might not go through liquid. For example, it might just jump straight from solid to gas, like sublimation. Of course, there are so many alternatives scenario that might happen, right? But for the most general cases, it will go through from solid to liquid and then to gas, right? But hopefully by seeing this graph or this curve over here, you see when and where you're supposed to apply Q equal to MC delta T and where you're supposed to apply Q equal to ML, all right? But that's the only two things that you need, okay? All right, nice. So with that in mind, so what can we do with this? So the thing is, we call it the conservation of energy, or in terms of heat transfer is a calorimetry. So what we have over here is this. Things start to get fun when you have two systems in thermal contact. Here we go. Remember thermal contact that we discussed last time? So that means you might have two sides of your system. One might have like some hot temperature. Some might have some colder temperature. So let me call it a T hot and T cold. Okay. So of course the temperature, the hot side is going to be greater than the cold side. So with this, then it means that you're going to have energy transfer from hot to cold. Energy will transfer from hot to cold automatically, right? Because they try to reach the thermal equilibrium. And now we understand this is, guys, Q. This is thermal transfer. This is the heat. This is the energy transfer that we have been talking about. This is heat. Okay. And this same amount of heat leave the hot part and enter the cold part. Cool. So that means if you take into account the amount of heat from the hot side, it must be the same thing as the heat that enter the cold side of this one. From the conservation of energy. I mean, the energy cannot just go anywhere, assuming that everything has already been sealed. So you only discuss about these two sides of the system. There's nothing else in the picture. You can think of this one as like an isolated system. There's no other way that the energy can transfer in other means. There's only just two parts of this one. So what I can conclude from here is, if you talk about the amount of heat that flow out from the hot side, it must be the same as the amount of heat that flow into the cold side. You guys with me? So to write down an equation for this, what I can do is I'm taking the hot part, calculating the amount of energy. This must be equal to the cold. Do you agree with this equation? With the sound effect. Do you agree with this equation? No. Why is not? Why not? Why isn't it not correct? Because it doesn't look like this one, right? Because of the sign. That's the key. So if you want to compare this one, I know what you're trying to do. When you want to compare this one, you want to compare just the magnitude, the amount of energy, right? You're supposed to put an absolute sign here, guys. If you put absolute sign here, this is perfectly correct because of the conservation of energy. The amount of energy flow out must be equal to the amount of energy flow in. Done. But then we already agree what happened to the heat flow. Whenever you have the flow out and whatever happens to the flow in, it has the opposite sign. Does that make sense? So if you talk about the Q hot is actually leaving So you might say this one has a negative sign into it. But then the cold side, the heat is flowing in, it has a positive sign associated with it. Or you can think in terms of the temperature change. The cold portion over here will rise in temperature. The hot portion will lower in temperature. So if you want to apply Q to MC delta T, one will be positive, one will be negative for sure. So that's why if you really want to take into account the sign, the correct equation has to be this. You have to put extra negative sign in the front. All right. You can use either expression, that's up to you. They will eventually mean the same thing. The way that we apply this one will be a lot clearer when we try to do the exercise. Okay, so let's give it a shot over here, guys. So let's do a simple one. All right, we might not be able to complete this one, but I think I will start setting up the equation for you, and then we can complete this question next time. All right, but at least I have something getting started for you guys today. So you have 500 grams of ice is added to an insulated cup that contains 200 grams of water. All right, so okay, you have, let me draw like a big one here. You have water over here, and you're just gonna throw a bunch of ice in here. There you go. All right, so with that, I can draw this one as a diagram. So you only have two parts over here. This part is ice, and this part is water. You guys with me? All right, in comparison on the right, that's your diagram. And of course, because the water is at 50 degrees Celsius, and it's 200 grams. Okay, and the ice is definitely at 0 degrees Celsius, and it's at 500 grams over here. So from there, you can see that there will be the heat transfer from water to ice. Does that make sense, guys? Okay, and because eventually, what is the final temperature? So what you can say is, all right, we don't know, but we assume it's supposed to be X. And X is supposed to be somewhere between either 0 or 50 degrees Celsius. They're going to meet somewhere in between. We don't know. Okay. So what you have over here is the temperature of the ice. Suppose it ends at X. So the delta T of the ice side, or the cold side over here, is going to be X minus 0. With me, guys? Final minus initial. Delta T from the hot side, which is water, is going to be final minus initial. Can you see what's going on right now? You can see that this one's supposed to be positive, and this one's supposed to be negative right there. Okay, so next time, what we can do is we're going to set up an equations to solve for X by using one of the two equations. You only have two equations to deal with. It's either Q equal to ML or Q equal to MC delta T, or just the combination of these two. Okay, by knowing these two equations, you should be able to solve for X, and you're supposed to be done there. Cool, guys? All right, so I think this is a good place to stop, and then I'll just have this one hanging over here for you to think about, and then we can complete this problem next time together. Sounds good? All right, guys, thank you for sticking around, and I'll see you guys next week, okay? And I will post the YouTube and everything. Just follow that playlist and everything. Okay. All right, guys. Thank you. I hope the sound is better now.